We're talking about chemical reactions today. We're going to talk in general about chemical reactions. I just need you to know the terms of the stuff that you start with and then the stuff that you end up with. And then we're also going to be looking at two special chemical reactions that are going to be coming up again and again and again in this unit. That's photosynthesis and cellular respiration. And they're coming up again and again through the course of the year. So that's why we're looking at those in particular. Living things undergo thousands of chemical reactions as part of the life process. So that's why we're looking at them. Chemical equations. Oops. Chemical equations, represent chemical reactions. So here's a chemical equation. You're making glucose, and so you know probably that you can't actually make glucose from things that you breathe in and things that you drink in, but plants do, and so do cyanobacteria, and so do certain protists. So this process is photosynthesis. The stuff that you start with, these things, are called the reactants. So reactants are shown on the left. This arrow means yields, as in this becomes this. So these things are what you produce, what you make. So hopefully you know the word produce is something that you end up making. So these things are called the products. Products are shown on the right. So whatever chemical reaction you have, the stuff that goes into it, the stuff you start with are called the reactants, and the stuff you end with are called the products, the stuff you produce. The number of each kind of atom must be the same on either side of the arrow, so the equation must be balanced. And we're not going to spend much time on this. I'm going to run through it once so you know what it means. This is a topic that you'll spend lots and lots of time on in chemistry next year. So we've got 6 carbons on this side, and look at this, 6 times, there are only 1 carbon in each atom of carbon dioxide, so you need 6 atoms of carbon. So that's all set. We've got our carbons. Now let's look at hydrogens. There are 12 hydrogens here, and look at this, 6 times 2, that's 12 hydrogens here. Oxygen, you've got 6 from glucose, and then there is atmospheric oxygen, molecular oxygen, and so that's O2. And there are 2 atoms of oxygen in each molecule of oxygen, and there are 6 molecules of oxygen. So 6 times 2 is 12, plus the other 6 is 18. So let's just write 18 here so we remember that for oxygen. On this side we have 6 times 2, that's 12 oxygens, plus another 6. 6 times just 1, you assume that that's 1. That's another 6, so you have 18 oxygens over here. So we are all set in the oxygen field as well. Bonds must be broken and or formed in order to make new compounds. When you break bonds, you can release energy. Here are some simple examples of chemical reactions. What I would want you to see from here are that these two things are called the reactants. This means yields, that means you make. This thing, your product, is the H2. In this example, you take 4 hydrogens plus carbon. These are the reactants, the stuff that goes into the equation. And you make methane, it's what you produce, so it's called the product. Energy flow in chemical reactions. Some reactions release energy, that means they give off energy, or get rid of energy, or expel energy. Why did that just happen? I don't know. Give off energy. Other reactions require energy, that they take in energy. Oh, so they require energy input. So here's an example with photosynthesis. So carbon dioxide and water, and then you add energy from either the sun or from your light bulb, and you make glucose. So glucose is a really high energy molecule. You can eat glucose and keep your body going or gain weight if you have too much of it. You can breathe carbon dioxide all day and drink water all day. It's not going to give you any energy. So you have this energy input here. So does the chemical reaction above release energy or require energy input? Well, here's your arrow. Everything before the arrow is energy that you're putting in. So this requires energy input. What kind of organism can do the reaction above? So you can pause and think about this for a minute. This is photosynthesis, photoautotrophs. That means Photo means light. Autotroph means they can make their own food, as opposed to a heterotroph. So there are a very, very, very few number of autotrophs that don't use sunshine or don't use some kind of light. But photoautotrophs do, so they do photosynthesis. Heterotrophs do not. They're things like you. They have to eat something. Fungi, students get this wrong all the time. Fungi do not require sunlight. They'll actually decompose stuff, so they'll live off of the decomposing stuff in the soil or whatever. You can tell this for two reasons. If you think about this for a little bit, um, I don't know if you know this or not, but mushrooms can actually be grown in caves, and so there's no sunshine in there, and so they can't be photoautotrophs. They can't do photosynthesis. Another example is athlete's foot fungus. If any of you ever had that, that's this kind of itchy thing. It makes your skin crack right between your toes or maybe another some other part on your foot. And it happens mostly when you have, maybe not in the summer when you go barefoot, but through the winter when you wear socks and shoes all day. Is there any sunshine getting to your foot? And the answer is no. So they don't do photosynthesis. They're actually eating the skin in your feet. Yuck. Some bacteria do photosynthesis, cyanobacteria. Some protists do as well, and then some don't. Plants certainly do. So all these things, some bacteria, not all of them, some protists, not all of them, and all plants are these things called photoautotrophs. Animals, nope. Algae, yes. So depending on your classification system, algae are often put in with protists, but anyway, give them their own separate place. Oh, look at this. I hope I agree with myself. Yay! Okay, aerobic cellular respiration. If you look at the picture a few back, all we did is reverse everything. So in this case, glucose is what you start with. You just ate it, yum, and you need oxygen. That's why you breathe. And then this is the stuff that you end up with. So these two things are the reactants in this case. Before they were on the other side of the arrow. These things are the products. Sometimes you'll draw it, whatever comes after the arrow. You'll see it drawn different ways, but whatever comes after the arrow is what you produce. The energy out we store in ATP, and we'll do a whole unit on that in a little bit. So does the chemical reaction above release energy or require energy input? You're getting energy at the end, so that means you're releasing energy. What is this energy used for? It is used for everything that you need. So everything that the cell has to do, if you grow, move, repair something, release secretions, whatever it is, move something across the cell membrane, everything that you do in your body that requires energy is going to be gotten through this ATP. Okay, so who does cellular respiration? Everybody. Not everybody does aerobic cellular respiration. Whoops. Whoa. Let me go back a few here. Yeah. Okay, so not every organism does aerobic cellular respiration, but when I have something similar to it, that's what I mean. So some just do fermentation, for example, but everybody does something where they're taking in glucose and releasing it. And that is the end of my story. No, it's not, because I have to tell you, let me just... one thing that students get confused with all the time is they say, okay, plants or any type of photoautotroph do photosynthesis. And so they think, we can add, the some bacteria and the protists and certainly add the algae in here. So some students will think, okay, these things do photosynthesis, so that means the other things are the things that do cellular respiration, and that's definitely not true. Why would a plant make glucose if it weren't going to end up breaking it down eventually so it can get its energy? The answer is it wouldn't. Why would it bother doing that? It wouldn't. So everything has to break down their sugar to make ATP. And that's true whether you made your own sugar, if you're a plant, or some type of photoautotroph. And it's also true if you had to eat something else in order to get it. And now that's the end of my story.